We finished that liquid drop model, but we have to do few problems. Okay. So first problem we are going to discuss that is related to mass parabola. Okay. So I'll finish. I'll do one or two. Two or three problems. Then I'll proceed for. I'll go to that cell model. I'll discuss that limitation of liquid drop model. Then I'll go to cell model. So let us solve problems. First problem you have. Okay. So it is given that you have an isobaric family of mass number A equals to 91. Okay. You have an isobaric family of mass number A equals to 91. That is provided. So in the first part, you have to calculate find Z naught. Okay. So find first Z naught that you have to find. In the part B, you have to calculate energy release in beta minus decay, that is Q beta minus energy release, because we already have discussed that Q value for beta plus or beta minus decay for that mass parabola, for any mass parabola, that will be positive. That's what I am saying, energy release, because for positive Q value that will be called energy release. Q beta minus, that is the energy release for transition leading to most stable isobar, means Z naught. In the C part you have to find. So find Z naught energy release for transition leading to most stable isobar. Please try to understand what is the meaning of this, leading to most stable isobar. The third part or part C, you have to calculate, find the energy release in beta plus decay for transition again leading to most stable isobar. This three parts A, B, C. Okay. Also, it is given the asymmetric energy coefficient that is provided 19 mega electron volt per c square. That is provided, and also AC is provided, Coulomb coefficient, that is 0.595 mega electron volt per c square. In addition to this, they have provided you the mass of a proton, that is 938.3 MeV per c square, that is provided. Okay. Also, I'm writing here mass of a neutron, that is also given 939.1 MeV per c square. The data that is provided. That can easily be done, right? Because Z naught we know that is minus beta by twice gamma. Okay. Now doing this problem, please try to understand this, leading to most stable isobar. So there is a beta minus decay. If I talk about part B, there's a beta minus decay leading to most stable isobar. What is the meaning of this? It means that parent nuclei is converting to most stable nucleus. Your parent nucleus and leading to most stable isobar means your parent nuclei is converting to daughter nuclei, and daughter nuclei is most stable. So first, if I calculate Z0 from here, then I can guess the value of Z, because to calculate energy release in beta minus decay, you need two parameters. Z, that is the atomic number of parent. Z0, this is for most stable nucleus atomic number. And leading to most stable configuration means parent nuclei is having atomic number that is Z0 plus on. Because आपको पता है बीटा माइनस डीके में क्या होती है? Sorry, beta minus that will be Z0 minus 1, right? That will be Z0 minus 1. In the part, again I am repeating. Beta minus decay, यहाँ जो लिखा गया है, you will calculate that Z0 first. है ना? तो बीटा माइनस डीके होके आपका डॉटर न्यूक्लियर जो बन रहा है, that is most stable nucleus. इसका मतलब पेरेंट न्यूक्लियर का एटॉमिक नंबर कितना होगा? पेरेंट न्यूक्लियर से डॉटर न्यूक्लियर जो बन रहा है, एंड डॉटर न्यूक्लियर इज मोस्ट स्टेबल. I'll come to one by one, that will be, then it will be clear. But you try to think about this. I'll come on.
Parent nuclei will be odd combination
No.
A.
You see here, mass number is given 91. From here, it is clear that combination either will be even odd or odd even. ठीक है ना? बट मैं यह कहना क्या चाह रहा था कि लीडिंग टू ट्रांजिशन, लीडिंग टू मोस्ट स्टेबल कॉन्फ़िगरेशन, इसका मतलब ये हुआ है कि जो आपका डॉटर न्यूक्लियर है, दैट इज योर डॉटर न्यूक्लियर इज मोस्ट स्टेबल न्यूक्लियर. यहाँ पे कोई भी बीटा माइनस डीके में पेरेंट और डॉटर कोई भी हो सकता है, राइट? डॉटर शुड हैव लो न्यूक्लियर मास. यहाँ पे इस टर्म और इस पार्ट का मतलब यही हुआ है कि डॉटर न्यूक्लियर इज स्पेसिफाइड that corresponding to most stable nucleus having atomic number Z0. तो बीटा माइनस डीके में एक्चुअली जो पेरेंट न्यूक्लियर है उसका एटॉमिक नंबर कितना है? एक्चुअली आपका पेरेंट न्यूक्लियर तो फिक्स, सॉरी डॉटर न्यूक्लियर तो फिक्स्ड हो गया, Z0 माइनस Z0 है. डॉटर न्यूक्लियर का एटॉमिक नंबर कितना है? Z0 है. तो ऑब्वियसली बीटा माइनस डीके कहां से शुरू होती है? लेफ्ट हैंड पार्ट से. और लेफ्ट हैंड का जो नाइबर है मोस्ट स्टेबल का, हाँ, नियरेस्ट जो न्यूक्लियर होगी उसका एटॉमिक नंबर कितना होगी? Z0 माइनस ऑन. यहाँ पे अगेन, यहाँ पे आपका फिर आपका जो स्टेबल न्यूक्लियर है और डॉटर न्यूक्लियर है, सी पार्ट में भी आपका कौन सा है? दैट इज योर मोस्ट स्टेबल न्यूक्लियर. और बीटा प्लस डी का कहां से शुरू होती है? राइट हैंड पार्ट से. एंड जो आपका नियरेस्ट राइट वाला न्यूक्लियर है, नियरेस्ट मींस नियरेस्ट टू मोस्ट स्टेबल, उसका एटॉमिक नंबर कितना होगा? दैट विल बी एग्जैक्टली. सो आई विल कैलकुलेट ऑन बाय ऑन. ये आपको समझाने की कोशिश कर रहे थे. इफ यू अंडरस्टूड नाउ, देन योर लाइफ इज सिंपल, यू कैन इजीली कैलकुलेट नाउ. ठीक है ना? इफ यू रेस्पॉन्ड मी, देन आई कैन चेंज माई स्पीड, है ना? कभी कभी पता नहीं चलती मैं स्लो जा रहा हूँ या फास्ट जा रहा हूँ, है ना? इफ यू रेस्पॉन्ड मी ना, देन आई कैन optimize that. Well, so data is given. Now I'll calculate that. In the first part, I'll calculate Z0. That is minus beta by twice gamma. if you remember beta, that was nothing but expression for beta, that is nothing but mp minus mn minus of 4 asymmetric energy, है ना. बट आपको याद है जब आपने बीटा को डिफाइन किया था, इट वाज लाइक इन द एटॉमिक मास यूनिट, बट यहाँ पे एटॉमिक मास यूनिट में गिवन नहीं है. यहाँ पे एटॉमिक मास यूनिट में गिवन है. यहाँ पे आपका एसिमेट्रिक कोफिशिएंट क्या गिवन है, एमईवी में गिवन है. हाँ, तो आपका एटॉमिक मास में गिवन नहीं है, सो यू हैव टू कीप दैट सी स्क्वायर हियर आल्सो. ठीक है ना, दैट यू हैव टू कीप इन माइंड. ठीक है ना. अगर ये एटॉमिक मास में गिवन होती देन यू हैव टू यूज ओनली ए, बट यहाँ पे एमईवी में गिवन है, ऑब्वियसली यू हैव टू कीप दैट 1 by c square. ठीक है ना. mp is given, that is 938.3, mn is given 939.1 and whole in mega electron volt per c square. And then you have 4 times, that is 19 by c square, and that unit is mega electron volt. I can see mega electron volt per c square in the both part actually. So this is your beta. If you calculate it, okay, if you calculate how much you will get minus 77 around, you know, 76.88 you will get. 76.8 you will get with minus sign. It means around 77 mega electron volt per c square. Okay. Again, if you see that gamma, that was like 4 asymmetric coefficient by A, and you have, then you have AC by A the power 1 by 3. Okay. And again, you have to keep, you see here also you have to keep 1 by c square, AA by c square, AC by c square, right? AC by c square, because here that they have given you in the unit of energy, that asymmetric and Coulomb coefficient, they have provided you in the unit of energy. So obviously you have to keep 1 by c square. So be careful about that. Okay. So I'll substitute that value. Everything you know, for A 19, then you have a 90 on. And then you have a AC, that is 0.595 divided by 90 on the power 1 by 3. And of course, unit क्या आ जाएगा? That will be mega electron volt per c square. That will be mega electron volt per c square, because this was given in MeV, so we'll have MeV common and 1 by c square is there. So if you calculate it, you'll basically get 0.96 mega electron volt per c square. Okay. Now I can calculate that Z naught. So that is minus beta by twice gamma, and you have minus here. In beta you have minus, and you have minus here also. Minus minus plus, so it will be 77 divided by 2 into 0.96, right? And I can see beta का भी आपका unit क्या है, MeV per c square, gamma का भी MeV per c square, and it is obvious because you are calculating number, right? So we calculate it, so that unit will be cancelled, right? MeV per c square in the numerator and denominator. As a result, you will get atomic number, that will be 4. So this is your first part. Okay. In the second part, now you have a beta minus decay. Now I can see, because your daughter nuclei is fixed, daughter nuclei is having atomic number 40. So obviously in the beta minus decay, the parent nuclei, or I can write like this, in the beta minus decay, there is a transition in the atomic number from 39, this will be your Z, to 40, that will be your Z naught, है ना? आपको याद है ये वाला, ये इक्वल्स टू क्या था आपका 91. It means this is corresponding to odd parabola case. मतलब पहले वाला डिस्कशन है, यहाँ पे एक ही पैराबोला रहेगा। सो +2 डेल्टा -2 डेल्टा का कोई सिनारियो नहीं है। +2 इन बीटा डीके +2 डेल्टा और -2 डेल्टा प्राइम, सॉरी +2 डेल्टा प्राइम और -2 डेल्टा प्राइम कहाँ पे आती है? जब आपका इवन दो मास पैराबोला होता है, जब आपका 2 मास पैराबोला होता है और वहां पे बीटा डीके होती है, देन यू विल हैव ए +2 डेल्टा प्राइम और -2 डेल्टा प्राइम फैक्टर। बट यहाँ से पता चल रहा है आपका ये ऑड मास नंबर के लिए है, जहाँ पे आपका सिंगल पैराबोला है। तो वहां पे जो आपका एनर्जी डीके का जो आपका फॉर्मूला, सॉरी क्यू बीटा का जो फॉर्मूला है, दैट वाज क्या था आपका? ट्वाइस गामा, राइट? ट्वाइस गामा एंड देन यू हैव z0 minus z minus half,
C square.
okay, into c square. Now I substitute that value. You have a twice, then gamma is 0.96, right? And you have a z0, that is how much? 40 minus z 39 minus half. ठीक है ना? दिख रहा है ये या नहीं दिख रहा है? दिख रहा है. 1 minute, I'll write it again. Okay. So if I again rewrite it, we'll have a q beta minus, and that will be twice 0.96 z z naught was there, that is 40, right? Then you have a z that is 39 minus half, okay? And that unit, you have a gamma here, that unit is mega electron volt per c square, and you have another c square was there, that will be cancelled, you know. And from here I can see this value will be actually how much? 40 minus 39, that is 1 minus half, that will be half. So this half will be cancelled with 2. As a result, you will have 0.96 mega electron volt. Similarly, in the part C, energy release in beta plus decay. So here I can see that your transition or transformation in Z, that will be like 40 on, that will be your Z to 40, that is Z naught, right? I can show here also pictorially if you want, like this kind of thing they are asking. You have a equals to 90 on, this side you have a mass, okay, nuclear mass of course, and this is your Z, and this point is your Z naught, that is 40, and so this side you have a 40 on, and this side you have a 39, okay. So this transition, that beta minus, okay, this is your beta minus decay, and this transition, that is your beta plus decay. They are asking about that energy release in that process. 39 to 40, that is your beta minus, and 40 on to 40, that is your beta plus. In that process, how much energy will be released? They are actually asking that. Okay, na? So again, if you calculate that q beta plus, so this will be twice gamma, right? Formula, if you remember, formula was twice gamma, that is 0.96. Then you have a z minus z naught in beta plus decay, right? So you'll have a z, that is 40 on minus z naught, 40 minus half, and of course that unit again it will be mega electron volt, right? C square 1 by c square will be cancelled, that unit will be mega electron volt, and I'll see that energy release again it will be, this 2 will be cancelled. If you combine this again, it will be half, and this 2 will be cancelled with this 2. As a result, energy will be 0.96 mega electron volt. So whether it is beta minus or beta plus, energy release will be same. It is like 0.96. But you have to keep in mind that this transition I'm taking for single parabola, and so you have to use that Q value. In this Q value calculation, you have to use that formula corresponding to odd mass number case, है ना? Even mass number अगर होता फिर आपको दो parabola draw करके you have to take into account that pairing term also, that is twice delta prime. ठीक है? Next question. Well, problem number 2. You have a Europeum EU 63 and mass number is 152 is fused with a neutron and is producing SM producing SM atomic number 62, mass number 152, and we have a proton. Okay, this fusion reaction is given. You have a europium fusing with a neutron and producing SM nucleus with additional proton. Okay, so also they have provided you that atomic mass of europium, that is given, that is 151.92 749 in the unit of atomic mass unit. Also they have provided you atomic mass. M atom means atomic mass of SM, that is 151.9 on 975. Okay, they have provided you the atomic mass of a hydrogen atom 1.00782 atomic mass unit. And also they have provided you the mass of a neutron, that is also provided, and that is 1.00866 U. These are the data they have provided you with that nuclear reaction. And they ask you to calculate Q value. And that Q value you have to calculate in the unit of atomic mass unit into C square. So you have to keep in mind, they didn't ask you to calculate in MeV, but they ask you to calculate in atomic mass unit. So you don't need to convert that unit here, okay? Can you do? Can anyone tell me what is the process? How will calculate that? In the class, can anyone tell me how will proceed?
Even number.
Aji?
Atomic mass is even number, sir.
See, interesting thing here. You have to calculate the Q value. No, I'm not asking about that. I'm not asking here that that factor. I mean, you are thinking like mass parabola, right? You're thinking about that mass parabola, and then you are trying to calculate that, right? But from mass parabola, if you want to calculate that Q value, did they mention that beta minus beta plus decay? Did they provided you that energy coefficient, like asymmetric energy coefficient or
Sir, from mass difference?
Exactly. From mass difference, what will do?
MA plus MB minus MC minus MBC.
That is expected, but where you will make mistake, you see they didn't provide you that nuclear mass. यहाँ पे क्या provided है?
Atomic
Atomic mass provided. So you have to convert that nuclear mass to atomic mass. First, you will write that Q value equation, and that you know in terms of nuclear mass. Then you have to convert that nuclear mass into atomic mass. So आपके पास एक एटम है, एटम में क्या है? न्यूक्लियस प्लस इलेक्ट्रॉन. तो न्यूक्लियर मास के साथ जेड नंबर ऑफ इलेक्ट्रॉनिक मास ऐड कर दोगे तो फिर क्या बन जाएगा आपका?
Atom.
Exactly. So I'll do that. You see how I'll do that. There, I mean, in exam they will never ask you difficult question, but there will always be some trick. You know that Q value equation, everyone knows, those who are preparing, है ना? But आपको थोड़ा ट्रिक, आपको पहले बताया था मैंने कि क्यू वैल्यू को लिखने का क्या प्रोसेस है, क्यू वैल्यू फाइंड आउट करने का, न्यूक्लियर मास सेपरेशन और न्यूक्लियर मास डिफरेंस, है ना? यहाँ पे क्या गिवन है आपको? एटॉमिक मास गिवन है. सो यू हैव टू कन्वर्ट दैट न्यूक्लियर मास इनटू एटॉमिक मास. ठीक है, दैट मच कॉन्सेप्ट इज नीडेड. दे विल नेवर आस्क यू डिफिकल्ट क्वेश्चन. जो डिफिकल्ट क्वेश्चन होती है बहुत कम होती है और वो बहुत कम ही लोग करते हैं एग्जाम में, है ना? आई एम नॉट डिमोटिवेटिंग यू, है ना, बट इस तरह की प्रॉब्लम ज्यादा आती है. ओके, so I'll write that equation, q value equation. So if I write that q value equation, you have a nuclear mass of europium plus mass of a neutron. See, I cannot ignore that mass of a neutron here because this is not an electron, right? It's massive. So I have to take into account this also. Then you have a nuclear mass minus nuclear mass of product, that is you have a Sm, you have a Sm and minus mass of a proton. And of course there will be c square factor. All about that energy, so m into c square. Right. Now see what I'll do. Nuclear mass of EU. Now if I add 63 times mass of an electron, I have to subtract it also, right? I can add, I can subtract. Now if you merge this electronic mass with nuclear mass of europium. Why I have added? Because the atomic number of europium is 63. So 60 nucleus of europium with 63 times mass of electron, if you combine, that will provide you the mass or atomic mass of europium. So in that way you have to convert, huh? Then you will have again mass of a neutron minus nuclear mass of Sm, है ना? Now see here, I'll subtract. 62 mass of an electron. I have to add 62 mass of a electron, and then you have a mass of a proton, and of course it will be c square. Sorry, you will have c square here. ठीक है? Now this I can write mass of a atomic mass of europium. This, if you take minus common, you will have atomic mass of Sm plus 62 times mass of a electron. ठीक है ना? तो इन दोनों को अगर कंबाइन करोगे, you will have remaining term this. You will have remaining term this. It means minus 63 Me plus 62 Me. मतलब कितना है? Minus 63 Me. That will be remaining. यहाँ से minus Me. Now you minus Me और प्रोटॉन को जोड़ोगे तो फिर क्या मिलेगा आपको? एक प्रोटॉन के साथ एक इलेक्ट्रॉन का मास जोड़ोगे, क्या हो जाएगा?
हाइड्रोजन एटम का मास.
Exactly. So I'll write like that. So I'll write atomic mass of europium, right? And you'll have mass of a neutron. Okay. Then you have atomic mass of Sm minus mass of a hydrogen atom into C square. Into C square. Okay, just you have to substitute that value. So I'll write here. So you have values like atomic mass is given, that is on 50 on 0.92 on 749, right? 749.
Yes, sir.
Then the mass of a neutron, that is 1.00866. Mass of Sm, that is on 50 on 0.9 on 975. And then you have a minus of mass of a hydrogen, that is 1.00782. And that unit will be atomic mass unit. You have C square multiplication factor also. You have a C square multiplication factor also, right? So whole unit, that is atomic mass unit, and you have C square multiplication factor also. Now if you calculate it, can you calculate and tell me how much you'll get? To calculate it, around you will get 2.8 10 to the power minus 3 atomic mass unit into C square. Okay. So this will be the Q value. So will there be energy release or absorbed? There will be energy release because Q value is positive. Okay. Now this is all about your liquid drop model and related problems. But liquid drop model is having some limitation. It cannot describe all that nuclear phenomena or nuclear properties. It can explain that energy release in Q beta decay, in beta minus decay or beta plus decay. It can explain or predict most stable nucleus for a given isobaric family. Okay, it can predict binding energy with very much high accuracy. So these are the application. It can describe beta decay. It can predict most stable nucleus for a given isobaric family. It can find binding energy of large number of nucleus with very high accuracy. But there is some limitation. The limitation is that it cannot predict nuclear spin and parity. It cannot predict nuclear magnetic moment. Okay, it cannot predict nuclear quadrupole moment. Quadrupole moment means electric quadrupole moment. So these are the properties that cannot be explained from liquid drop model. Also, it cannot explain that magic number. Okay, these are the limitation of liquid drop model. And to resolve that problem, there is another model that is called cell model. So you have a cell model. इसको ये भी बोलते हैं इसको, that is single particle cell models. Single particle cell model. It basically came in 1945 to 1950. Or it is called single particle that I'll come. Okay. So the experimental observation, first I'll discuss. Observations. So observation number 1. It is observed that if any nucleus contain atomic number like 2, 8, 20, 28, 50 or 82. So if any nucleus contain atomic number or number of proton like either 2 or 8 or 20, 28 or 50 or 82, they are found to be most stable. Also, if any nuclei contain neutron number like 2, 8, 20, 28, 50, 82 or on 26, they are also found to stay. They are also found to be most stable. So if any nuclei either contain atomic number like 2 or 8 or 20 or 28 or 50 or 82, or if any nuclei contain this many number of number of proton, or if it contain neutron number like this 2, 8, 20, 28, 50, 82, 186, they are found to be most stable in the nature. So they are basically called what? They are basically called magic number. Also, है ना, कोई न्यूक्लियाई इस नंबर ऑफ प्रोटॉन कंटेन करे और इस नंबर ऑफ न्यूट्रॉन कंटेन करे, या if any nuclei contain proton and neutron number like 2, 8, 20, 28, 50, 82 on 26, they are also found to be most stable, है ना. तो कोई भी न्यूक्लियस either proton number this much or this many, or neutron number this many, or neutron and proton number this many, they are found to be most stable in the nature. अगर कोई न्यूक्लियाई either proton number और neutron number ये वाला कंटेंट करे, उसको हम क्या करेंगे, what I'll call that nuclei or that number, I'll call that number is your magic number. But here, if any nuclei contain both proton and neutron number 2, 8, 20, 28, 50, 82 or 126, then I'll call that will be your double magic number. Double magic number. So if any nuclei contain magic number or double magic number, that will be most stable, that is observed to be most stable in the nature. Then nuclear scientists said, definitely there will be cell structure inside nucleus. There is definitely some cell structure inside nucleus. That's why they are more stable. Because why they are predicting like this? Because we know from electronic configuration or from that atomic concept, if you remember, that if you have an inert gas is more stable, right? Why? Because they have a closed cell structure. Because atomic structure is having cell structure, and for inert gas that cell is completely closed. That's why they are more stable. So that actually they are thinking, if this is happening in atomic physics, like you have an electron is having cell structure means electron is actually arranged in a cell, 1s2, 2s2, 2p6 like that. तो जहां पे जिस atom का last cell completely closed है, for example you have an inert gas, their last cell is completely closed, so they are more stable. So they are thinking like that. This similar similar phenomena is happening inside nucleus also. For nucleus, for some nucleus, there is a outer shell is completely closed, and that's why they are more stable. And closed shell is happening, they're predicting actually closed shell is happening in that number. So that's why they are basically more stable. So they are thinking like that. Also, there are other observation also. This is the first observation. The second observation, you have observation number 2.
Sir,
Haji,
sir, what is the meaning of stable?
stable.
इस मतलब स्टेबल मतलब इलेक्ट्रॉन में सॉरी एटम में जब स्टेबल हम बताते हैं कि वो रिएक्शन कम करते हैं, इसको हम स्टेबल कहते हैं. न्यूक्लियर में
There will be no decay, right? I mean, I'll come to that point. Suppose मान लो आपके पास एक रेडियोएक्टिव सीरीज है, आपने पढ़ा होगा ना रेडियोएक्टिव सीरीज, एक्टिनियम सीरीज, नेपच्यूनियम सीरीज, यूरेनियम सीरीज. सो देयर इज ए रेडियोएक्टिव डीके, है ना. और वो डीके होते होते जो लास्ट न्यूक्लियाई बनते हैं, लाइक फॉर एग्जांपल लास्ट जो न्यूक्लियाई होते हैं रेडियोएक्टिव में अगर देखोगे, सो देयर इज ए रेडियोएक्टिव डीके, आइदर अल्फा और बीटा डीके. डीके होते होते जो लास्ट न्यूक्लियाई बनते हैं, दैट इज आइदर लेड और बिस्मथ. और उनके पास क्या है, उनके पास मैजिक नंबर है. आई मीन उनके पास आइदर प्रोटॉन नंबर और न्यूट्रॉन नंबर दैट इज कॉरेस्पॉन्डिंग टू मैजिक नंबर. इट मींस they will not further decay, they are stable.
Okay, sir.
They will not further decay. Second observation, the number of stable isotones. Number of stable isotones are maximum when a nuclei contain that neutron number either 50 or 82, है ना. तो if any new, I mean that number of stable isotones, you know that definition of isotones, right?
Equal number of neutrons.
So that number of stable isotones are maximum if any nuclei contain that neutron number either 50 or 82. Why? Because this number corresponding to magic number, right? They are actually most stable. If any nuclei contain that neutron number like 50 or 82, that is actually they belongs to magic number, so they will be most stable. So this was actually observation. Third observation, you have a number of stable isotopes. Number of stable isotopes are maximum when if any nuclei contain that number of proton, that is either 20 or 50 or 80. Any nuclei contain this many number of proton, they are stable, है ना. So number of stable isotopes, isotope means same atomic number. तो यहाँ पे शायद आपको if I am correct, यहाँ पे number of stable isotopes corresponding to 50 or 82. It was like you have a 6 number of stable isotopes, है ना, either for 50 or 82. और इस नंबर के लिए आपका जो आपको मिल रहा था number of stable isotopes, that was 5. It's obvious because this number corresponding to, again, your magic number. Then most abundant element in the nature, can anyone tell me most abundant?
Hydrogen.
No. How can you think that most abundant? Most abundant means most stable, right? And for most stable, again, that number belongs to magic number.
Helium.
Magic number. So I cannot say I mean hydrogen. Why? Because hydrogen
Helium.
does not have any magic number. So if you see that most abundant element in the universe,
Iron.
iron. In the universe, I'm talking. So most abundant.
Hydrogen.
Haji,
Hydrogen and sir, hydrogen element.
in the universe. टोटल यूनिवर्स की बात चल रही है. टोटल हाइड्रोजन ज्यादा है. Most abundant elements in the universe, that is not hydrogen. That is either oxygen 8, 16 or calcium 20, 40 or sorry, not or, these are the most abundant element. 82, lead 82 or 208. It contains both proton number and neutron number magic number. This is also both proton number and neutron number magic number, proton number and neutron number magic number. So they are basically double magic number nuclei. Okay, and this is the most abundant element in the universe.
So abundant means easily available. Most available, no sir.
Most available.
Okay.
So that belongs to your again magic number. Okay, so this is the observation. Then I'll come to tomorrow. I'll discuss about that cell model. Okay, because already time over. Okay, but tomorrow class is very important for your net purpose. We'll discuss that model and we'll solve that problem.
Sir, helium also double magic number, no?
Helium also double. Helium also double magic number. But it's not abundant. But that abundant is element corresponding to magic number. That is the main thing. है ना? जैसे सारे जो आपका आइसोटोन्स मैक्सिमम सारे जो मैजिक नंबर के लिए नहीं मिला, 50 और 82 के लिए मिला है. But that observation actually saying that these nuclei are most stable जब आपका that number belong to either that number belong to magic number. Magic number में ये phenomena हो रहा है. So that actually giving hints that you have a nucleus is having closed cell structure. Tomorrow we'll discuss then it will be clear. Okay.
Thank you, sir.
Thank you, sir.